I think I started the recording, so.
Thank you very much. And good morning for those of you who are connecting from North America and South America. Good afternoon to those of you who are connecting from Europe, and good evening to those of you who are connecting from the Asia Pacific area. We have a fantastic webinar today. My name is Paolo Bonato. I'm the editor-in-chief of the IEEE Open Journal of Engineering, Medicine, and Biology, which we launched 4 years back. So this is our volume number 5. And we had the distinct pleasure of having a fabulous series of papers, which we call a special series, because we have a volume per year, but it's essentially a special issue that Dr. Jung from the UK organized as guest editor. So I'm going to switch off my camera and I'll let Dr. Jung take the lead from here. I look forward to the talks of our distinguished speakers. And thank you very much for connecting today for our OJEMB webinar. Dr. Jung.
Thank you. This bear with me, let me share the screen. Okay, there we go. And good morning, good afternoon, good evening to all the attendees from all the countries over the world. First, I need to thank the editor-in-chief who gave us a chance to organize this meeting. We received dozens of papers, and we just selected the best of our paper, and we tried to give the most advanced progresses, and they are all coming to understand. And first I think is from Professor Liu from Hubei University, and he will give us like a report on in-house the small and imbalanced wound their effort can help detect the wound, and then this can definitely reduce the mortality and to help save lives. Now, Professor Liu, can you hear my voice?
Yes.
Okay. I will switch the camera to you, and feel free to speak to our attendees.
Okay. Can you see the PowerPoint?
Yeah.
Okay. Hello, everyone. I'm Liu Shuaiqi. I come from Hebei University. My topic is NF-GAT, a doodle feature-based graph annotation network for ASD classification. First, let's begin introductions. First, let's understand what ASD disease is. ASD is neurologic disorders of brain functions in which patients suffer from many symptoms, such as social dysfunction and repetitive behaviors. Currently, the diagnosis of ASD mainly relies on diagnosis of doctors using cognitive scales, which is time-consuming and subjective. So our goal is to recognize ASD using graph annotation network. The development of medical imaging have provided new ideas for diagnosis of ASD. Amongst them, fMRI is a non-invasive and can objectively present the state of the brain. It has high spatial and temporal resolution. Our method is construct based on fMRI. This is the flow about how to construct brain structures based on fMRI and Pearson correlation coefficient. This is the idea for constructing a FGAT model. We give a new way to construct node filter based on fMRI data. The node filters are mapped by a function and then weight summed. And the experiment shows that the FGAT can better improve the classification performance. Then is the overall framework. The model is divided to two parts. The upper is the construction of node filter graph. The bottom is based on graph attention layer to learn noodle filter and classification based on full connected layer. This is the mathematical senior of the GAT layers. This is the attention coefficient, and this is the softmax. This is the cross correlation coefficient. This gives the classification. This is the detailed information about the test public dataset, which is the name is ABID. We compared our model with several other advanced ASD classification models and verified the effectiveness of the model. Other models include traditional methods, non-graph deep learning method, GCM method, GAT method, and our method. From this table, we can find that our method achieved the best effort except sensitivities. This is the ablation experiment that shows the effectiveness of each part of our method. We further show the impact of different outliers on the models. The left picture is the information of different atlas. The right picture shows that the HO atlas we have chosen achieved the best result. Then is the conclusion. We proposed a method named NFGAT, which uses fMRI data to define node filters and graph attention network to recognize ASD. The results show that our model outperforms other models. Thank you for your listenings. My topic is closed.
Thanks, Professor Liu. I need to apologize because I just noticed there were 3 Lius in our special issue. Yes, so I think you have done an excellent job in detecting the ASD. Now, let us they have some questions also from our panelists. And if you have any questions, feel free to drop to the chat box, or you can directly ask via the microphone. Professor Liu, I received a question from our attendees, and they asked, can you introduce the background or like the current in China.
The last sentence is so blurred. I cannot listen to very clearly.
Yudong, I'm sorry, I'm interjecting. Could you make sure that the microphone is close to your mouth, because sometimes the cancellation software
Okay.
prevents us from listening to what you're saying.
Okay. Yeah. Let me repeat the previous question we received from our attendees. Their request of Professor searches in China about the autism spectrum, the autism spectrum disorder.
I'm sorry, I can't understand. I can't listen it clearly. Is the question that how many layers of the JT did you choose? Did this model choose to obtain the deep filter?
Yes.
Oh, okay. In our model, we choose 2 layers of JT to train our model. After evaluations experiments, we found that 2 layers of JT can be better extract deep filters and then relative fewer redundant filters, which can make our model have a good diagnostic effort. When the number of the layer increased, it will maybe will overfitting. That's all.
Yudong, there is a person among the attendees who actually raised their hands. I'm going to allow that person to talk.
Yeah, please.
Dr. Zhu, unmute yourself.
Hello, Professor. Can you hear me?
Yeah, please.
Yeah, go ahead.
Please.
Hello, Professor. I have a question. What's the form of the model input signal?
Okay, thank you. The question is, what's the form of the input of the model? I
Yes.
think the time source is the form of 2-dimensional matrix. It's the FC matrix. The 2 coordinates represent the number of brain regions and the number of time points respectively, and the number value represents the dependent value of the blood organelles, and the computer functional connectives is also in the form of 2-dimensional matrices. Both cardinal represent the numbers of the brain regions, and the numerous value represent the cardinal value between the 2 brain regions. That's all. Thank you.
Okay, thank you, Professor. I understand.
Okay, thank you.
Professor, let's wait a few more minutes, and I guess there will be more questions. And dear attendees.
So there is another person you don't raise and Dr. Lee,
yeah.
but the hand was actually lower, I guess. No, it's up. Okay. And why don't we take one more question and then we
Yes,
move to the next.
One more question, yeah.
So Dr. Lee, unmute yourself.
Hello, Professor. Can you hear me?
Yeah, we can hear you.
I'd like to ask what are the advantages of using graph structure compared with traditional algorithms?
The question is what's the advance of using graph structure?
Yes.
Okay, thank you. Firstly, the experiment results show that higher accuracy can be obtained by using graph structure. Secondly, it's more intuitive and interpretable to simulate the brain with graph structure because there are many alters. Finally, the graph structure can fully consider the reactions of brain signals, which is very important for brain analysis and disease diagnosis. Thank you. That's all.
I see. Thank you, Professor.
Okay, thank you. And also, dear Paulo, from my side, I can't see the list of the attendees. Maybe I do not have the authority to see who raised their hands. Let's move to the next.
I'll keep track. I'll keep track of anybody who raises their hands. Don't worry. I'll let you know. Okay.
Okay, thank you.
Okay, thank you.
So I think the next speaker is from Professor María. Okay, let me check it. Yeah, from Professor María, and first, you know that. Let me check it because there are so many. Okay, and I believe like the title of the paper is deep learning based glucose prediction models. So María, please unmute yourself.
Okay, thank you. Yeah, I'm gonna share my screen. And please let me know if you can see the slides. Can you see the slides?
Yeah.
That's perfect. Thank you.
Perfect, thank you.
Please.
So today I'm going to present our paper on deep learning based glucose prediction models. The main idea of this paper, as many of you might know, is to build better models for glucose prediction, in particular for type 1 diabetes patients. So as you know, diabetes is a global public health concern, and there are many people diagnosed with diabetes type 1, and this number is increasing over years. So for these patients, something crucial is to maintain blood glucose levels in a correct level. And what they have to do at this point is manage it with insulin administration. So there are many devices now, like the artificial pancreas, that help controlling these levels. So the idea is we have to measure the glucose and we have to administer the appropriate amount of insulin for the given glucose that we have now, but more than the given glucose that we have now, for the glucose that we will have in like 30 minutes, because we know that there is a delay in the time the insulin is administered and it reaches the bloodstream and starts decreasing the levels of blood glucose. So there is definitely a need for improving these predictions. The current methods that are implemented in the insulin pumps nowadays are only based on previous glucose levels. So they basically measure with these sensors, like the one we're using here. They measure the history of glucose and they predict what's going to come next. What we wanted to investigate in this study is whether if we introduce new inputs such as food intake and exercise, we could predict this, we could improve these predictions of our models. So what we did, we took ambulatory data from 20 participants. We tried this data to be as natural as possible, so we didn't ask for any restriction on diet or exercise. We asked the patients to just continue their normal life, and we monitor them. We monitor the glucose, and we monitor the exercise and sleep with this smartwatch. And also they register all the food intake for 1 week long each participant. So with this, we had like a pretty granular database on different data altogether, and we could, with that, build different models and compare among them. So basically, we collected this glucose data. This is the amount of food they were consuming, and something that we also registered for diabetic patients is the insulin that they were administering, either with a pump or with any kind of insulin form. And we have here the heart rate that are correlated with the exercise levels and the number of steps they were performing per day or per minute or per hour. And as you can see, we have these two groups, diabetes patients and healthy patients, because we wanted to also see how the models perform in these two different groups that have a pretty different glucose behavior. So we trained different models, and we also tried different approaches. So our approaches for this, we consider population training. That what we did for that is taking the 20 patients all together, all the data together, and build a model with this data that could be used for any additional individual. Even this population training had like two populations. So we did train separately glucose, diabetic patients and healthy subjects. Then we built other series of models that were personalized. So for each subject, we only used their data. And of course, we had some data for training and some data for validation, but the data for the whole training were from the same patient. And then we used the fine-tuning approach that where we used the data from the whole population, but then we fine-tune these models with the population, with the personalized data for a particular patient. So the main idea of this is, or we can say, well, the main advantage before any training we can see to the population approach is that we have more data. We have data from 20 subjects in this case, but it could be definitely increased. The main advantage of the personalized training is that the data are tailored for these patients, so it should work better. But on the other side, the negative aspect is that we have less data. And the fine-tuning would be kind of a middle ground where we have more data for building the structure of the model, and then we can fine-tune it with data from one particular patient. And then performance was assessed with root mean square error, and we also used the Clark error grid that I'll show you later, and that is commonly used in glucose research or diabetes research. So we also considered 5 groups of variables. For the first group, we only consider the traditional approach, that is using only the previous values for the glucose levels. For the second group, we used the previous glucose levels plus information about the caloric intake and the carbohydrates intake and the insulin that was administered. For the third group, we also increased heart rate, and the fourth included also steps, and the 5 was similar to the 4, but without the information about nutrition. So with that, as I previously said, we categorize in 2 groups, and the 2 groups have pretty similar characteristics, demographic characteristics. Also 50% women and 50% men, so the data was pretty balanced in that regard. So something that was interesting to see is that even if we ask the subjects to register all the energy intake and all the food they were having, we noticed that the energy intake that they reported was lower than expected from resting energy expenditure. So this might indicate that we have a systematic underreporting of energy intake that is pretty common actually in research. People tend to underreport what they eat, and not really on purpose, they tend to forget, so it's very difficult, and it's a critical point to be addressed in all these types of research. So something also important in our publication is that we made available for the scientific community this database. So it's freely available for anybody to continue trying to improve models and use this data for their own research. And this is the results for the different models. So also something that was pretty surprising for us, we were expecting the model with all the information that was modeled for to perform better. And indeed, it performed better, but not that much better than we expected. And we think that if introducing the energy intake doesn't help that much, it can be due to this underreporting that we were observing. So maybe the people are not reporting the correct amount of carbohydrates they are having, or they are not reporting correctly the times. And for this kind of models, timing is key. So if they are reporting the food after they consume it, or reporting too early, then the model is not going to be able to use this information properly. Regarding the models, we did see differences. So this encoder-decoder model was the one that performed better, and this happened in both healthy and diabetic patients. Also, something that we observed is, if you only look at this, the root mean square error for diabetic people is much higher than for healthy subjects. But this is also because the levels of the glucose levels for diabetic people are much higher than for healthy subjects. So the errors are also higher. And we can also see more variability for the personalized models than for the population models, because they have less information. So in total, if we look at this, the personalized models do not work that well, are these 5 in the middle. That's probably because the amount of data is not enough. We still collected 1 week of data, but this might not be enough. So definitely the population, or even better, the fine-tuning approach, are the approaches that work better in this context, because they take advantage of the whole information of the population, but then also they allow us to fine-tune with this particular data. So this is the Clark error grids that I was introducing before. So mainly what they show is the reference blood glucose and the predicted blood glucose. They show us the error, but they also show us how far we are from the healthy zone. So we can say that A and B are healthy zones. They don't pose a risk for our subjects, but if we reach zones like E or E is definitely a dangerous zone, and even D starts to be pretty dangerous. Those are zones that we want to avoid. So in glucose prediction, we not only want to make good predictions, but it's also very important to keep our subjects safe. And if we tell the controller that the glucose is going to be very, very high, we might have too large bolus of insulin coming into the system that could definitely harm the patient. So we need to avoid these extreme zones. And in conclusion, we can say that the deep learning methods are effective for building these models. Population-based worked very well, and personalized models did a good job, but they still have a lot of variability. So for some subjects where they also had like maybe more data, or they were informing the food better, they worked well, but other subjects were performing a little bit not that well. And fine-tuning approach emerged as the most effective and robust method, especially in these scenarios where data availability varies. So this is all from my part, but I'm very happy to answer questions if you have some.
Okay, thanks, Maria. And from your slide, I just noticed like there might be like a small typo in our website, and you can see from the website when it shows the URL of your dataset, it has like a suffix like called the online. Maybe I will for me I will contact our copy editor website editor to remove those extra words.
Absolutely, I'll do that, no problem.
Okay. Let's wait for some like questions.
So I don't see questions in the Q&A box. Do you want us to move to the next talk?
Okay, yeah. So I think because like various like talk are self-explanatory and quite clear. So I guess our attendees all understand fully. Thank you, Maria. Thank you.
Yudong, I just noticed in the chat there is actually a question that just came up. Maria, can you see it?
Yeah. I see like Dr. Sames asked a question. Thank you for your interesting talk. Is there any information on the minimum glucose data points needed for training the personal, the personalized model? Yeah. So,
so based in our experience, I could say that at least 1 week of data is needed. Of course, it really depends on the variability of the data, on the quality also. Like sometimes what we also found is that we might have missing data, whether you have disconnections, that's also very critical. But if you have like good quality data, 4 days of data could start working for training a good model and getting good accuracy. We mainly, when we were using 1 week of data, they were working well. For some patients, as I was saying, we had some missing data within that week, and for those might not work that well. And also, some patients, for example, were having like very uncontrolled glucose levels, and for those, it's definitely more difficult to predict. But I would say roughly 1 week of data, 5 days of data, something like that.
Okay. Okay, thanks. Particularly, I believe the cumulative data set is helpful for all the community researching the type 1 diabetes mellitus. I think they are quite useful. Thank you again. So now let's move to the final talk. So I think the final talk is from our last Professor Chunrong Huang, right? So Professor Huang, would you please unmute yourself? Yeah.
Oh, okay, thank you.
Yes,
Okay,
we
can
can
you
see
see my
your
screen?
screen now. Yeah. Please,
Okay, thank you. Okay. Good afternoon, ladies and gentlemen. I'm Chunrong Huang from National Yang Jiao Tong University. Today, I would like to present our paper, Gastric Section Correlation Network for Gastric Precancer Region Diagnosis. Okay, so for the diagnosis process of the endoscopy will use the endoscope, and the endoscope will pass through the patient's throat and the esophagus to the stomach, and then capture the images in the stomach for the diagnosis. So in the right side, you can see there are 3 main parts. The first part is called entrance. The second part is called the body, which is the midturn of the stomach. And the third part is the cardia, which is the upper part, upper section of the stomach. These 3 parts will record the important information for the gastric diagnosis. So usually the doctors will capture images of these 3 parts. So for given a close look for these 3 parts, you can see that the capture direction, the direction of the cameras will be different. That is, the viewing angle will be different for different patients, especially in the body part over here. So you can see different kinds of body parts shown in these images. And you can also see different kinds of entrance parts. And you can also see the textures and the color responses of these entrance parts are different because the lighting condition. So you can see the lighting condition is variant, and also the textures are variant in the endoscopic images. So when we want to perform any diagnosis in the endoscopic images, it is necessary to overcome the lighting condition and also the scale changes in these images. In our work, we want to solve the gastric precancer lesion diagnosis problem. So what is the gastric precancerous lesion? It is a lesion that occurs before the cancer. So it is very important to be diagnosed, because if you have this lesion, which implies that you probably will get cancer in the near future. So it is necessary, the patient needs to keep on monitoring so that we can find the cancer as early as possible. And one of the most important gastric precancer lesion is called corpus predominant gastritis index, in short CGI. It is used to assess the gastric cancer risk. Okay, the index is based on the acute inflammation and chronic inflammation of entrance, body, and the cardia. That is the 3 sections we mentioned above. So how can we compute CGI? That is, we want to compare the inflammation scores between the entrance part and the body part. If body part has serious inflammation compared with the entrance part, then the patient has CGI. And if the cardiac part has severe inflammation compared with the entrance part. And also the scope of the cardia is larger than, is not equal to 1, then the patient also has CGI. If the patient has CGI, which implies that the patient has higher risk to have gastric cancer in the near future. Okay, so how can we diagnose CGI in clinical? Currently, it requires invasive biopsy. That is, we need to get the tissue sample from your stomach. So we need to sample a tissue, for example, from here, and then the tissue is examined by pathologists. It usually requires several weeks to have the information. So it is a very time-consuming process. Moreover, when we take the tissues from the stomach, it usually causes bleeding. So the bleeding will also hurt the patients. So do we have any method to replace the biopsy and also diagnose CGI? So this is the goal of our paper. That is, we want to diagnose CGI from the endoscopic images. But the question is, the CGI, the diagnosis of CGI is based on the correlations of entrance, inflammation between entrance and the body, and also the entrance and the cardia. So we need to develop a network to represent the correlations between these gastric sections. So to achieve the goal, we propose the gastric section correlation network. Here, the input of the network would be the 3 images, including the image of entrance, image of body, and the image of cardia. And then to overcome the scale changes showing in the above slides, we developed the scaling feature fusion module. It contains 3 different modules to calculate features of different scales. For the largest scale one, this network will train the features of the largest field of view from the entrance, body, and cardiac images. And then at the end of the network, we have a channel attention layer over here to extract the salient features. And then we have a pooling layer to generate the median image, and then use the median network to generate the features for the median scales. And finally, we have a small network to generate the features for the smaller field of view. And then for each gastric section, we concatenate the features from 3 different scales so that we can have features to represent the gastric sections from different fields of view for entrance, body, and cardia. And now after we get the features from the entrance, body, and cardia, we want to consider the correlations among different gastric sections. So the features of these gastric sections are sent to section correlation module. So for the first one, we consider the features from entrance and the body for the CGI diagnosis. And then we consider the features from entrance and cardia for the also for the CGI diagnosis. And after the design based on the equation we show above for the CGI, we also consider how about consider the correlations of all of the 3 gastric sections. So we develop another loss function and another subnetwork in the section correlation module to consider the features from entrance, body, and cardia simultaneously to compute the CGI. So this is the section correlation module. By consider both the scaling feature fusion module and section correlation module, then we have the gastric section correlation network. So in our experiment, we collect more than 300 patients from 2 hospitals. And here are the details about the data sets. And here are the ablation studies for 3 dominant modules. So for the scale fusion, scaling feature fusion modules, channel attention modules, and also session correlation modules. So of course, with more modules, the accuracy will increase. I would like to show for this row. This row shows that the session correlation module without considering the entrance body and cardiac simultaneously. So you can see without simultaneously consider this part, the accuracy will drop. However, if you consider the correlations among entrance body and cardiac simultaneously, then the network can learn better and achieve better accuracy. And here are the comparison for the state of the art. Because recently, there are no methods for the CGI diagnosis. And for the standard networks, usually we have one image as the input. But however, for the CGI diagnosis, we need to have 3 images. So we concatenate the endoscopic images of the patients from the entrance body and cardiac to a 9-channel image and perform 1-by-1 convolution layer to learn a 3-channel images. And then these 3-channel images input to the following classification network for comparison. As you can see, this network do not consider the correlations among the endoscopic images, that is the entrance body and cardiac. So their accuracy are not satisfactory. However, the proposed method achieves significant better accuracy, sensitivity, specificity, and also the AUC compared with state-of-the-art methods. Now here are the qualitative results. As you can see, the variations of the entrance body and the cardiac compared with the images showing above. So here is the confidence value showing above in the image. As you can see, our method achieved the most confidence value and also achieved the correct classification for the entrance body and cardiac for the CGI diagnosis. So we also developed a system for medical doctor usage. So the medical doctor can upload the images of entrance body and cardiac. And then our system will automatically show the attention map that is from the channel attention map from the channel attention layer to let the doctor know that which part is the focus part by the network. And then we also show the cancer risk based on the confidence level of the CGI classification results, so that the doctors can diagnose CGI in, I think, 1 or 2 minutes, instead of using the traditional biopsy methods, which requires more than 1 week to obtain the CGI results. And in conclusion, we propose the gastric session correlation network for purpose predominant gastritis index diagnosis. There are 2 main modules are proposed. 2 main modules are proposed, and we hope these modules can assist the endoscopists to diagnose the precancerous regions in an easier way and more efficient way. Okay, thank you for your listening.
Okay, thank you, Professor Huang. And I just checked the time zone. I think it's now quite late in Taiwan. It's about 11 p.m., right?
Yeah, it's okay.
Yeah, so I think all of us are greatly appreciate your willingness to present at such a late hour, because it means a lot to us that you adjust your schedule to make this talk possible. Thank you. Now Are there any questions from our attendees? Feel free to raise your hand.
It's my pleasure to give the talk. So thank you for the invitation. Any questions? Any questions are welcome.
So I don't see any questions in the
Okay,
Q&A box.
Maybe I can ask like a question to Professor Fong. So for the gastric section correlation network, so why do you think like the section correlation is important in your effort?
Okay, yeah, because from the formulation of the CGI require the comparison between two different gastric sections. It compare the information from two different gastric sections. So we believe that it is necessary to compare the correlations between two different gastric sections to obtain the information of CGI. So that's the reason why we developed the gastric correlation session.
Okay,
Yeah.
thank you. So now,
You're welcome.
okay, thank you. Because now we have all finished all the talks. Let me return the microphone to Paulo. So
Thank you very much, Yudong. I think we can wrap up the webinar at this point in time. I'm going to encourage attendees to contact the speakers if they have additional questions that they want to ask offline. I want to thank Dr. Zhang for organizing these special issues. These are 3 of the many papers that were published as part of these special issues that Dr. Zhang guest edited. I want to thank the speakers one more time and thank the attendees for being here today. Yudong, if you don't have any closing remarks, I think we can close this here and ask Federico and Virginia just to stop the recording.
So I think we need to thank like all the authors, all the like editors, and all the the managers, like the room manager and many other things. But maybe like it's not my time to. But I just really want to appreciate my my thanks to all of them.
Thank you very much, and thank you again to the attendees. So we can close the room at this point in time.